Okay, so we have to start. This was the point where we stopped last week, and I think I'm going to start from this point. So let me just go back a few slides. Um, okay, we had some sample and test questions that I pleaded that on our individual time we should do them, and if we have challenges or difficulties, we can then talk about them in this class. Um, I want to assume that most of us have done it. The solutions we have provided, I don't know if there were questions. Did anyone in the process of attempting to do um, um, the questions maybe encounter some challenges that you're not able to comprehend or not able to, get your way around it? Okay, I want to assume that we all, for everyone that attempted, I want to assume that the process was okay, was clear, you're able to understand. However, if at any point you still have challenges, please come back and we can always address this. So we're still talking about motor, and in the last Saturday we looked at the formulas, for calculating the energy conversion. Essentially, motor converts electrical energy to mechanical energy, and we saw the formula for doing converting to kilowatt mechanical. And we went through all that process. Now let's look at energy efficiency in the motors, how energy losses occur in motors, and what is actually going on, when these conversions are taking place. So one of the things we're going to be looking at today is sleep, motor sleep, and other behaviors. Okay, so sleep is the percentage difference between the synchronous speed of the motor and the rotor speed. Um, Now let me try to explain this in a basic way. We know that motor operates based on flux. I think a combination of magnetic and electrical flux. So I mean that actually induces the rotation, the mechanical rotation that we see. So that's the rotation of the flux, right? Is then attached to a rotor, right? Now, sometimes the speed of that of the flux can vary from that of the rotor. The rotor can also be the shaft that you're seeing. I mean, the shaft where you can now attach maybe your belt and every other thing, right? So the difference between that flux, that magnetic flux, the motor, and the rotor is what we know as a slip. They may not be going on at the same speed. So for example, the synchronous speed of the motor may be, for example, 1,500, and the rotor speed will be maybe something like 1,450. So there's a gap of 50 in number, right? So that is what we call slip, and that's what we call motor slip. So this slip, induces some level of inefficiency in the system. Now, a simple way to understand this clearly is your generator. I'm sure most of us, um, even for some of us that uses solar now, at some point we're using generator. When you start your generator, you've noticed that the speed, it's always high, but when you add load to it, you notice that, I mean, there's a change, in the sound, right? So those are the things that also, so those are the kind of impact, your load will have on the speed of the motor, right? So, and when you begin to notice something like this, when you begin to add load to the generator, you increase the sleep. You actually increase the sleep, and we are going to see how that we are going to see the calculation to that. But I just want you to understand, the basic definition or understanding of what when we say sleep, the basic, meaning or definition of sleep. So now this chart is just to help us understand the relationship between maybe the efficiency, the power factor, the load on the motor, right? The current and then the sleep. So here you have on this vertical axis, you have the power factor or efficiency of the motor, right? And here you have the percentage loading. So the more you begin to load the motor, the sleep will keep on increasing. And that's why when you load your generator, if you notice that the sound will just drop, right? If you measure the decibel of that sound without a load, it will be high. But once you add a load to that generator, the sound will somehow drop, right? So once that sound drops, what happens is that the sleep will begin to increase. So you begin to have, some skips between the synchronous speed of the motor and the rotor speed. So that's what this means. And of course, the more when you begin to add more load, the current also increases. You can see the current. It also increases. And then the good thing is that once this is happening, your power factor is improving. Okay. And that's why when you underload your motor, your efficiency is usually low. Now this highest curve here is the efficiency. You can see that the efficiency is highest, maybe at from this point, maybe about 70, up until you get to like 100. If you load your motor above 100, you're on your own, you begin to reduce the efficiency and you also put that motor at risk, at danger. So this is just to help us understand that relationship. Now let's look at how to calculate that slip. Now this is the formula to calculate the slip. If you want to calculate the motor slip, if you're going to be conducting an industrial energy audit, most times you might not be able to, depending on the depth of the audit. Sometimes there's what we call maybe an isolated audit. So, for example, a client can say, "Look, I want you to just audit this particular production line, and that production line might be motors." So, in some instances, you might need to do this. If you need, like I said, depending on the depth of the audit and the analysis that you're supposed to do, right? But if you're just, when we're going to talk about levels of energy audit, you're going to see different categories of levels of energy audit. So if you just maybe walk through energy audit or level 2 energy audit, you might not, at some point, you might not be involved in all of these calculations. But like I said, it all depends on the objective of the audit. But it's good you understand this. The good thing is that when you understand this, even without carrying out some of this, calculation and test, you'll be able to see, based on the understanding that you already have, you'll be able to know that, oh, something is wrong here. I need to do more, I need to do more detailed analysis of this process, because you already know that there is something that is going wrong in that process. Based on this understanding, then you can now say, okay, I need to, dive more into this analysis and do more detailed audit of this process. And at that point, you can now begin to do all these calculations. So now motor slip is equals to the synchronous speed. When I say synchronous speed, the speed of that flux, that's electromagnetic flux, right? Minus the speed of the rotor, that shaft, minus the speed of the shaft, divided by the synchronous speed, that's the speed of that electromagnetic flux, right? So synchronous speed is equals to, now this is, I'm trying to define what this synchronous speed is. So how do you calculate this synchronous speed? So the synchronous speed is equal to the frequency times 60, right? No, here in Nigeria, our frequency is 50, right? So frequency is most times 50, but if in other countries, maybe US, I think it's about 60, but thereabout, it's country dependent, but in Nigeria, it is 50. You're going to divide it by the number of pole pair. Pole pair means if you're told that your pole pair is 4, because you're pairing them, this number of pole pair will now become 2. If you're given that your pole pair is 2, because
sorry, please, the screen is hanging, it's not changing, it's still the same.
Yes. I'm still there, but I'm talking about this formula. Can you see the formula? Can you see my cursor moving? Can you see my cursor moving?
Yes.
Yes, I can see it.
Yes. So I'm still here. I'm still on the first slide. I'm talking about this number of pole pairs.
All right, noted.
Yes. So in some given instances, or if you look at the data sheet of that motor, and you see that the pole pair is 4, what you're essentially going to put here, what you're going to be dividing by is 2, because you're pairing it, right? If you're given that the pole pair of that motor is 2, then you're going to put 1 here, right? So if you translate that into the formula, it becomes frequency times 60 divided by the pole pair. Now let us see a worked example. But before that, I just want to show you this is a picture from the generator I showed to you the other time. If you look at this generator, you can actually see the RPM, the engine speed is 1005 RPM. So some of these you can even see them from the generator. So this is an engine speed. You can see 1500 RPM, right? So let us look at a sample question here. So here we have a sample question. For a 4-pole induction motor operating at 50 hertz, the slip at a shaft speed of 1450 RPM will be what? Okay. The question again, for a 4-pole induction motor operating at 50% hertz, the slip at the shaft speed of 1450 RPM would be what? So using the formula that I share with you, right? Now let us first of all calculate the synchronous speed. The synchronous speed, like I say again, is the speed of electromagnetic flux. So let us calculate that first. And it's the frequency. The frequency was given as 50. We have a constant value of 60 here. You multiply by that 60 divided by the pole pair. We are told that it's 4. So here we're going to have 2. So if you multiply 50 by 60 divided by 2, you're going to have 1500 RPM. So this is the synchronous speed of that motor, right? So now we are given the speed of the shaft, that the rotor speed or the speed of the motor. We are given that it's 1450. Now, how do we calculate the slip? The slip is the synchronous speed minus the rotor speed divided by the synchronous speed. And when we substitute our values, we're going to have 1500 minus 1450 divided by 1500. And that gives us 3.33%. So the motor slip is 3.33%. So if this value increases, then you have more losses. If this value increases, then you have more losses. So the more the inefficiency, that's what that simply means. So this is another sample question. I'm not going to do so much because this is a straightforward calculation, right? I don't want to do so much on this. The solution is here. You're going to get this. You can see that this one now, you can see that the motor slip is as high as 9.2%. So the higher the motor slip, the more inefficiency you have in the system. So how does losses occur in motors? How does the inefficiency of motors, how does it happen? And these are the list of the various ways in which this happens. You can see the iron losses, you can see the winding losses. A lot of motors, you can see some of the industry, a lot of time they have been gone for rewinding. So when you do this, you actually reduce the efficiency of that from the standard at which it was produced. Then you have the rotor losses, which is just what we describe now, the synchronous speed and the rotor speed. You have the rotor losses. You have frictions and ventilations. When motor is operating, it gets hot, it gets heated, and this heating is as a result of maybe the electromagnetic flux and the resistances, in the operation of the motor. So it gets heated, and if not well ventilated, the temperature can increase. So all of these are the processes of inefficiencies in motor. And then you have the last one, which is load depending on additional losses. Depending on how you load a particular motor, it can increase. So if you underload a particular motor, you're actually increasing the losses, right? But if you load a motor properly, maybe at 60, 70, 80%, right? 90%, then you're optimizing, efficiency because you're loading it properly. At that point, at an optimal loading, even if the motor itself is inefficient, but by optimal loading of the motor, you actually improve the efficiency of that motor. Okay. So here are just some of the standards, efficiency standards in motors, right? So since June 2011, the IEC standard 60034 that is the IEC is the International Electrotechnical Commission. So these are the various efficiency ratings for motor. So if a motor is rated IE4, right? That means that it has the highest efficiency, super premium efficiency. The lowest efficiency is IE1, which is the standard efficiency, right? But as an auditor, we are not always quick to recommend change of motors. I think I said this before, we are not always quick to recommend changing of motors. However, we always look at the motor-driven applications. There's a lot of energy savings that can be achieved from the motor-driven application instead of just changing the motor. When you change the motor, yes, you're going to achieve an efficiency improvement. However, it might not be significant. It might not be significant compared to the efficiency gain that you will get when you look at the motor-driven applications and you try to implement energy efficiency measures. So there are different levels of loading motor, and I think I've explained this that if you overload motor, now this is just trying to explain this in a more basic form using maybe a truck. So you can see that the truck is overloaded. When you do this, actually you impact the efficiency of the motor. You reduce the efficiency. You increase overheating, reduce lifespan, and may fail regularly. It will lose energy in form of heat, resulting to low energy efficiency. Then if you underload the motor, it will run at a fraction of its specified power and draw excessive and inefficient electrical current. As the current does not supply useful energy, efficiency is low. Now, when you load a motor nominally, that's the best way to do that, So when you go out to an industry and you see a motor, sometimes by just having this knowledge, you can see if a motor is underloaded or overloaded. However, there's an instrument to also, determine this. There's an instrument that you can use to check, the speed of the motor. You can now compare, compare that with the nameplate, and then you can be able to see, the efficiency, the loading percentage, right, of the motor. So effect of voltage variations in motors. From the beginning, we talked about imbalance in voltage, right? So how does this affect motors? Okay, so voltage drop. If you have a voltage drop, right, it causes motor inefficiency. Of course, motor efficiency will drop. It will affect the power factor. It will affect the running current and the temperature. Now, when you don't have when you have a low voltage, that's when there's a drop in voltage. What motors, this electrical equipment, what they will normally do is that they will draw excess current to compensate for the voltage. Remember that power is equal to voltage times current. Power is equal to voltage times current. So power is a combination of voltage and current. So when the voltage is low, it will draw excess current to compensate for that shortage in voltage. And once that happens, you begin to have increased heating, of the motor, and you have higher losses. So if motor terminal voltage is below the rated voltage, okay, I've just explained this, it will draw more current than the rated current, which will ultimately result in overheating of the motor. This also happens for an air conditioning system. Maybe some of you, because I practice this, I become more intentional about energy. So I have this conventional air conditioning system, and I have a meter attached to it, so I can actually see the current. I can actually see the voltage that it is drawing. So I have noticed that sometimes when the voltage is low, I notice that the current will be higher. It will draw more current. But once the voltage begins to increase, the current will begin to drop, right? So this is just essentially what happens in motors. When the voltage drops, it will draw excess current. And with more current that it draws, it leads to inefficiency. So, I talked about voltage imbalance, in our previous class. And here is just, more like a standard, like if your voltage imbalance is within 1%, it is okay. But if it goes beyond that 1%, it causes current, current unbalances and thus losses in terms of heat. I think I've explained this already. So what can be done beyond, and what beyond the motor? I've already explained this already, where I talked about instead of recommending changing of the motor, sometimes you have to look at the motor-driven application and some optimization measures. So we're going to look at some of those things that can be done at this level. So optimizing potentials for the motor itself are rather limited. Much more can be achieved in the system that the motor is driving. Okay. So here we are looking at So this green line, the green column, right, is actually showing some of the measures that can be implemented. Now, these measures are motor-driven application, not on the motor itself. Motor-driven application that can be achieved, right? So you can see some of the things that can be done is pipe dimensioning. Assuming that the motor is used for pumping, right? Now the pipe through which the fluid or the liquid flows, you have to dimension it properly, okay, so that you can get the best out of the motor. That is one. Two is armature or valves. Sometimes you go to the industry, normally you will definitely find valves. What does valve do? Remember that motor is to increase motor produces pressure. Remember, I mean, if it's for pumping, right? Okay, it's still right. I'm going. You can say I'm good to go. Can you hear me? Sorry for the slight interruption there. Can you still see my screen?
Yes.
Okay.
Yes, we can see it.
Okay. So I was talking about some of the measures that can be applied. So some of the motor-driven application could be for pumping purposes, right? So if it's pumping purposes, I've talked about the proper dimensioning of the pipes. Now, what does the motor do actually? For pumping purpose, it's actually meant to produce pressure, right? It increases the pressure of the fluid that you want to pump, right? So that's one. Then what valves do is to actually reduce pressure. I mean, think about the purpose of having a valve along a piping system is to reduce pressure, right? So if there's a way for you to avoid the use of a valve, because the motor is actually increasing pressure and valve is doing the counter of what the motor is doing, right? So in some industries, they have different need of they have the fluid to be flowing at different pressure, at different levels. But maybe that fluid is being generated by a single motor. So what will normally happen when it gets to the point where they will use valve to reduce it to the pressure that they want it to be flowing into their production process, right? So you have to look at those things. Is it possible to find a way to reduce or eliminate to some certain level the use of those valves? If you're able to do that, what's going to happen? You're going to actually reduce the power consumption of that motor, or you might need to downsize the motor. If the motor is too big for the purpose, you might need to downsize that motor. So these are also part of the possibility or energy efficiency measure that you might want to look into. You might also want to look at the operating hours of the motor. If the motor is running and there's no production that is taking place, then it needs to be, I mean, you need to stop it. I have been to some industry, you can see an idle motor operating. I mean, something should be going on. So for example, okay, now this is not for motor, this is for ironing, because I've been to a hotel, you go to a laundry section and, the iron is heated, the people who are supposed to be ironing are not ironing, they're just, just having some conversations or not even, or maybe they finish ironing and they forget to turn it off. But this kind of thing can also happen when you're working in motor systems. Sometimes the motor might be running and it's not doing any meaningful work. So at that point, it needs to be shut down. So now that is things that can be done on the motor-driven applications. Now there is another segment of the motor system, which is the drive chain. We are going to come to this. There are different types of drive chain. Now, drive chains are what you use to connect that mechanical energy that is coming out from the shafts to what you want to drive. So if you want to drive a conveyor, you might need a belt to connect the shaft to the conveyor so that you can transfer that mechanical power to the conveyor that you want to move, right? So here are some of the things you can do. There's what we call VSD. VSD means variable speed drive. Some motors run at full speed, but when you implement a VSD measure, you can actually regulate regulate the speed to the level that you want it. I want you to look at this like inverter type air conditioning system. Now, the difference between an inverter type air conditioning system and the normal conventional air conditioning system is that for the inverter type air conditioning system, you can regulate the speed. You can speed it up, you can lower it. That is the only difference between the inverter type air conditioning system and the conventional air conditioning system. So I think for the inverter type air conditioner, I think it works on DC motor. So for the fact that it works on DC motor, I think you can be able to vary that speed, right? But for the normal conventional air conditioning system, you cannot regulate the speed. It's just, start and stop. Anytime it's running at full speed. When you meet the required temperature, it stops. But for the inverter type, you can reduce the speed, and once you reduce the speed, it reduces the power that it's consumed, and that's why inverter air conditioning system saves energy, because you can reduce the speed and then you reduce the energy it consumes. You can have an inverter air conditioning system running at maybe 200 watts, okay, but I doubt you can't see a conventional air conditioning system running at 200 watts. It's not possible. Even, it always comes at full speed. So now, if you now look at, so this is essentially what VSD do for motor system. When you introduce a VSD in the motor system, you can now vary the speed of that motor. So you can now reduce the speed of the motor to the requirement that you want it to operate. Another one is gearbox. And then the next one is pumps. The next one is vents. Now these are for the, these are for the drive chains, like the equipment or the instrument that you use to transfer the speed that is coming out from the motor, that is the mechanical speed, to whatever you want to drive. Now, for the motor itself, what can you do? You can do proper dimensioning of the motor, that is, proper sizing of the motor. If the motor is too large for the work it's doing, you can actually recommend a lower size, motor. Or if the motor is overloaded, you can recommend a higher. So this is what proper dimensioning means. Then the next one is the IE class. I already showed you the IE class. You have about 4 levels of IE class. The highest is IE4, which is the premium standard. And these are the impact of the measure. So you can see that the largest impact, the largest saving you can get is from the total system application, right? And the medium impact you can get is for the chains, the drive system. And changing the motor alone is only going to be minimal. Like I said this earlier, we are not always in a haste to recommend changing of the motor. But if there is justifiable reason to recommend that, please, you need to recommend maybe changing of the motor, either improving the IE class or increasing the size or reducing the size. These are the low and high cost measures of motors. So the low cost measures for energy efficiency in motors are shut off motor during peak time of electricity demand. If this is acceptable for the consumer anyway, you can't just shut off motor when a production needs to be going. But if the production can be varied, you can then decide, okay, during peak time, this motor should not be running. Now, switch off consumption from high tariff time to low tariff time. It's important as an energy auditor to also understand the tariff structure of your client. How are they being charged? Is there a time of use? Of course, in Nigeria, we don't have time of use, but that does not mean that it may not come on at some point. But imagine that you go to other countries and there is time of use tariff. Okay, so it's always good to have to look at the tariff structure and then advise based on when some of the motors should be running. That is if the production process can be variable, then you can make this recommendation. They use synthetic lubricants for large gearbox. Now, these are low cost measures, right? There are also high cost measures, which include the use of variable speed drive. We already explained this. Replacement of an oversized motor by appropriately dimensioning new motor. And the replacement of an old inefficient motor by higher or high efficiency motor. I've already talked about this. Now, let us look at drives. There is a motor and there's a drive. Drive is what you use to transfer that mechanical energy to what you want to drive. So here, drives are used to transfer mechanical energy of motor to their driven applications. I already explained this. Now you have direct drive, direct coupled drive, right? Now this is what it is. If you have a direct coupled drive, efficiency is always, I think efficiency is always higher. However, this might also create problem depending on the system you want to drive. Okay. Now there are chain driven applications. You can see there are chain. This is applicable for some, so like I know motorbikes, you have use chain to transfer the mechanical energy, and for some of them you have belts, right? And some of them you have gear drives. So these are just to make you understand that there is a motor and there is still another element that is actually used to transfer that mechanical energy to the driven application. Now, what are the low-cost measures for this for these drives? Now, check tension of the belt every 3 to 6 months. If you go to industry, you see that many of the motors, some of them are driven by belts. Sometimes the tension of the belt, is such that it is loose, it's not properly tensioned, and once that happens, you begin to lose efficiency in that process. Lubricate and maintain gears according to specifications. Replace V-belt with notched or synchronous teeth belt drive. Now, these are some of the measures you can implement for the drive system. Now, for the high cost measure, it's just simply to replace the gearbox, especially one gear type, with a VSD or direct drive motor. For a direct drive motor, the efficiency is usually high because there's no losses between the shaft and the drive. There's no loss along that part. Now let's look at pump. For many of us, we are going to mistake pump. We may not have that clear understanding between pump and motors. And here is a simple question I want to ask. Are pump the same thing as motor? Are they the same as motor? When we talk about pumps, are they the same as motors?
No.
Okay, thank you very much. So they are not the same thing. So a lot of time when we talk about pumps, we assume that they are the same as motors. And simply because a lot of time both are coupled together. Because they are coupled together does not mean they are the same. They are not the same. Pump is a motor-driven application. I say that again. Pump is a motor-driven application. Okay. Now we're talking about pump because when you go to the industry, there's a lot of fluid movements, and these are done by pumps. So you have a motor that drives the pump. So now we talked about the motor. Let's talk about the pump. We need to understand how pump works. Now the beauty about an energy auditor is that you understand the science behind these technologies. And the moment you understand the science behind this technology, then you understand how they consume energy. And for that reason, you can actually tell, when a process is not efficient, right? So I'm just saying it just so you can understand the reason why we need to understand what is going on in a pump. So a pump has some parts that are attached. The major part of a pump is an impeller. The major part of a pump is an impeller. Impeller is what actually, pushes the fluid, by its rotation. And this rotation is now, this impeller is driven by the motor, right? So as the impeller rotates, it pushes the fluid. Now, the bigger the impeller, the bigger the fluid it can move. The smaller the impeller, the smaller the fluid it can move. That is 1. 2. The higher the speed of the impeller, the higher the volume of fluid it can move. The lower the speed of the impeller, the lower the volume of fluid it can move. That is 2. 3. The higher the speed of the impeller, the higher energy, the higher power it draws. The higher the speed of the impeller, the higher energy it consumes. The lower the speed of impeller, the lower energy it consumes. Okay, so we're going to see how all of this relates together, how there's a formula that combines all of this together. Remember, I have talked about 3 things, right? I've talked about the diameter of the impeller, I've talked about the speed of the impeller, and I've talked about the energy consumption of the impeller, right? So we're going to come to see how all of this relates. But there's another part of it, there's the 4th part of it, which is the height that you're pumping, right? The height of the fluid you're pumping. Remember, when you're pumping a fluid, in as much as that fluid is going horizontal, even if it's going on a horizontal pipe, there is a way to calculate that horizontal length into a height, okay? So we're going to talk about it. So first, there are two kinds of heights of when you're pumping. No, the first one is pumping demand. Pumping demand is defined by static height. Static height. When you talk about static height, I want you to look at this. Look at this first diagram here, right? Now, this is the pump here. This is the fluid. You're pumping it from this low level to this high level. Now, what is the static height? The static height is the difference between the high level and the low level. That is the static height. Okay, now keep that on one side. Now, there's another height. There's a dynamic height. Remember when I talked about you pumping a fluid through a horizontal pipe? Okay, in as much as it's a horizontal pipe, there is a dynamic height attached to it. And what is this dynamic height? It's the flow. Remember, when the flow is flowing through the horizontal pipe, it's also flowing against friction. There's a frictional losses. So there's a friction that is trying to overcome. So those dynamic height is those frictional losses. The valves, if there are valves along the pipes, it's a friction. These are losses. So we count them as a height, but they are dynamic heights. If there are bends, I've been to a water processing company industry, and the bends along the flow is just so much, and some of these bends could be avoided. So the thing is that every bend that you have induces loss into the system, because you need, I mean, every bend is like a speed reduction, right? So the more bend you're able to avoid, the more you're able to maintain the pressure of the flowing fluid, and the more it can get to its destination, more quickly and in more volumes. So the pipe diameter is also another dynamic height that needs to be overcome, right? So now all of this dynamic height is explained in this second diagram, right? So this is your pumping starting point, and then this is your finishing point, right? But along the line there are dynamic losses, friction, bends, pipe dimensioning. So this is the second type of demand height. So for pumping, this is a simple equation for calculating pumps. This is a very basic equation. Now, this is a kilowatt. Now, this kilowatt P is the P here is the shaft speed of the motor. But in the case of a pump, it is the kilowatt P, which is the pumping, right? But however, remember that this kilowatt is coming from a motor. It is output from a mechanical motor, right? Now, it's not an input into the pump. So as an input into the pump, it is the kilowatt P. It's the same thing as the kilowatt mechanical output from the motor. Now, the Q that we have here is the liters per minute. Here is the liters per minute. And then the H is the height. Remember when I talked about dynamic height and the static height? The H is the height. And then you have a constant value of 9.8 divided by 6,000 times efficiency. Now, the efficiency here is efficiency of the pump, which you will find at the nameplate. The nameplate of the pump, you find it, right? So
why the 60,000?
Is a constant value. Is a constant. The 60,000 and the 9.5 is a constant value, right? Just in the same way that when you're doing when we're doing calculations for heat flow, you will see that the specific heat capacity of water is 4.2. Okay, anyway, that's empirical, right? It has been experimented and they arrive at that value. In the same way, this 60,000 is a constant value.
Okay.
Yes, so that's just the best explanation to that. Unless if you want us to go and begin to see how this formula was derived, then we can now begin to see how this 60. But this is the equation that we need to know. We need to do some of these calculations.
We can go on, no problem.
Okay. So important savings can be obtained by lowering the flow rates. I've talked about this, reducing the head, that is the height of the pumping, and operating at the best efficiency point of the pump. So this is just a simple example. So what is the load on a pump on a pump motor with a flow rate of 9,000 liters per minute with a head pressure of 110 meters. So you're pumping at a height of 110 meters. Now, if the pump efficiency is 83%, now all you need to do is just extract these values and then you put them into this formula and then you have your answer. Some of these things are straightforward calculation. The most challenging calculation you're going to have, if, for example, for those of you interested in doing your CEM or CA, one of the most challenging calculation you're going to have is on motors. Not on motors, sorry. It's going to be on heat transfer. You know, it's a little bit dynamic and tricky. Yeah, but some of these things are just straightforward calculations. Electricals are straightforward calculations. So if you have these formulas, you just extract whatever you have been given, and then you can get your answers. So the action of the power, you know, the kilowatt peak, and that's what we've just done here. We've calculated it, and this is the shaft power required to operate the pump. So if you need to size a motor for this pump, you should be looking for a motor that have this output. That's what this simply tells you. You should look for a motor that have this 195 kilowatt mechanical output. In that case, it will now serve as an input into the pump. So this is the power that is required to operate this pump. The pump that can do 9,000 liters per minute at a height of this, you know. So now let us look at affinity laws. Remember when I talked about, you know, impeller diameter, when I talked about impeller speed, and when I talked about energy consumption. So a fine scientist, you know, has been able to put this together, you know, and it's known as affinity laws. Affinity laws are the laws that help us to understand the relationship between impeller diameter, impeller diameter, the speed of the impeller, the height of pumping, that is the meter that you want to pump, and then the quantity of water that you can get, or fluid rather, because it can be anything. When I say fluid, it can be water, it can be anything, it can be diesel, it can be anything, right? So this is affinity laws help us understand that relationship. And in this case, Q stands for the flow, that is the flow of the fluid. N stands for the rotational speed of the impeller. D stands for the impeller diameter. And H stands for the height in terms of meters. And P means the power consumption, right? Now, affinity law says that if you divide the flow, now, what affinity law is trying to help us to do is, what happens when there are changes? If you change the flow rate, how does it affect the rotational speed of the impeller? How does it affect the impeller diameter, right? That's what affinity laws try to help us do. So when you see Q1, Q2, it means Q1 means the original flow rate, right? Then Q2 means the adjusted flow. So if, for example, the flow was happening at 9,000 liters per minute and you reduce this to 7,000 liters per minute, how does it affect the impeller speed? How does it affect the impeller diameter? If you need to, for example, if you need to redesign the impeller diameter, what should be the size of the impeller diameter such that you maintain an optimal efficiency? Okay, so we're going to work an example to help us understand all of this. But the affinity law is now trying to tell us that the original flow divided by the adjusted flow is equals to the now the N here is the rotational speed, is equal to the rotational speed of the original rotational speed divided by the adjusted rotational speed. It might sound a little bit confusing, but there's an example. We're going to work an example to help us understand this. Now, the height of the pumping, the original height of the pumping divided by the adjusted height of the pumping is equal to the square, is equal to the rotational speed, the original rotational speed square divided by the rotational speed adjusted, divided by adjusted rotational speed, square of the adjusted rotational speed. Then the power consumption is equals to, the original power consumption divided by the adjusted power consumption is equals to the cube of the original rotational speed divided by the cube of the adjusted rotational speed. Okay, so effect of impeller diameter keeps rotational speed constant. So let's just avoid all of this. Let's work out an example so we can understand what is actually going on. So here's an example one. A centrifugal pump is driving 200 meter cube per hour. 200 meter cube per hour is actually the flow rate, right? Now the impeller diameter is trimmed. What this is saying that the impeller diameter is, you reduce the impeller diameter by 10%. Now the question is, the new flow, remember the original flow is 200 meter cube per hour, right? Now they're not asking what will be the adjusted flow rate when you reduce the impeller diameter by 10%. Okay, that's what this question is asking us. So what do we know? We know the original flow rate, which is 200 meters cube per hour. This is the volume of fluid that they can pump per hour. Now, we are told that the impeller diameter was reduced by 10%. So we are not told the original impeller diameter. But in this case, we can assume, so let us assume that the original impeller diameter is 100, right? Now, if you reduce it by 10%, it will now become 90, right? So now we know the original impeller diameter and we know the adjusted impeller diameter. What are we looking for? We are looking for Q2, the new or the adjusted flow rates. So once we can be able to identify this, we can now look for the formula that connects Q1, D1, D2, and Q2. So we can now go back to this formula that we had. All right. Now this one is for this is for the rotational speed. This second one is for the impeller diameter. So we can see that this first formula that we have here has Q1, Q2, D1, D2, and we know what Q1 means, we know what Q2 means, we know what D1 means, and we know what D2 means. So this is the formula we're going to use to solve this question. So when we apply this formula, what we're going to have, because we already know what the Q1 is, we know what the D1 and the D2, we're looking for Q2. When we substitute into this formula, right, we're going to arrive at 180 meter cube per hour. 180 meter cube per hour. So what this means is that if you reduce the impeller diameter by 10%, keeping the rotational speed constant, the flow will reduce from 200 meter cube to 180 meter cube. I don't know if this makes sense. It might sound a little bit confusing because we are dealing with a lot of terminologies here. It might sound a little bit confused, but I mean, when you go through this on your own and when you go back through these videos and you're still confused about it, please, the WhatsApp group is there. Please come back to the WhatsApp group and then we can see how to, help you understand this better.
Hello, sir.
Yes, please.
Okay, the diameter of the impeller, is this something that we can easily change, or this is just for theoretical consideration?
So the whole
can
idea,
can we conveniently change the impeller of an existing motor? That's what I'm asking.
okay. Now the reason why this is sometimes you might need to resize a pump. Now there's a motor that drives this pump, right? Now if you look at the load that the industry is, the fluid that is being pumped or the fluid that they are pumping, right? Sometimes there might be need for you to redimension the pumping or the pumping section. You don't necessarily need to change the entire motor. You just need to change the pump, so that it can align with the load that it has. Now, if this happens and the motor is already oversized, It is also recommended that the motor be fitted with VSD. So you can also, vary the speed of the motor, and then you can now properly dimension the pump that is required based on the load. So for example, if you go to an industry and they are pumping 9,000, meter cube per hour, right? And the pump essentially can do like 30 meter cube. But the highest that this industry have done is 9,000. But that pump is designed to do 30,000. In that case, you can then advise the proper dimensioning of that pump. And how do you advise the proper dimensioning of that pump? Is by doing some of this calculation. So you can now say, okay, this is the proper dimension that you need for this pump, because based on the height you're pumping, based on the volume, the flow rate that you're pumping, this is the pump that I think is an ideal for this process. I don't know if you understand. You might not necessarily be, I mean, like the impeller diameter is not something you can, in as much as if you want to retrofit the pump, I mean, if it's possible to get a different size of impeller diameter that has the same, fittings for the pump that you already have, yes, it's possible to change it. Just change the impeller diameter. However, if you need to recommend the change of the entire pump, then you need to be able to run this calculation and say, okay, this is the proper pumping size that is required for the application. I don't know if that answers your question.
Yeah, thank you. Yes, clear.
Okay. So here is another question. This is a centrifugal pump operating at 1,440 RPM. Now this is the rotational speed. This M in this case. If the power if the power is to be reduced by 75%, now what is in this case now, if power is to be reduced by 75%, now in this case, assuming that you have a pump, I have a motor that is driving that pump, and that motor has a VSD, and you reduce the speed of that pump from the VSD by 75%. That's what this question is asking you. Now you're reducing it by 75% of the existing power. Now the speed of the pump as per affinity law will now become what? The speed of the pump was, so we know the original speed. It was 1,440 RPM. Now you reduce the speed, you reduce the power from the motor using a VSD, you reduce it by 75%. Because how will this reduction impact the speed of that pump? What will be the new speed of the pump? That's the question they're asking us, right? So there's a formula that connects the speed and the power. All the formulas are stated here already. And that's what affinity law helps us to do. It helps us to understand the relationship between all of these variables. Now, this is a formula that connects the power and the speed. So this is the formula we're going to use in this question. So we use this formula. Now we know what the P1, so what is the P1? Let me see. If the power is reduced to 75%, so we don't know what the P1 is, but we know what it was reduced. It was reduced to 75%. Right? So it was like 100%. You reduce it to 75%, right? So essentially, our P1 is 100%, and it was reduced to 75%, right?